Hello, my name is Bob D. Hilster, and I am your particle model guru. Today's video is about the hammer and feather, which David Scott, the astronaut, did on the moon as a demonstration of acceleration of different objects in a gravitational field. If you're new to the particle model, I suggest that you watch these two videos, the particle model overview and the levels of the universe, and you'll get a better idea of what I'm talking, because each individual video assumes a certain amount of background of information. I don't re-explain everything else. This whole thing started with Galileo. A biography by Galileo's pupil, Vincenzo Vivani, stated that Galileo had dropped balls of the same material but different masses from the Leaning Tower of Pisa to demonstrate that their time of descent was independent of their mass. This was contrary to what Aristotle had taught, that heavy objects fall faster than lighter ones, in direct proportion to their weight. While this story has been retold in popular accounts, there is no account by Galileo himself of such an experiment, and is generally accepted by historians that it was at most a thought experiment which did not actually take place. But David Scott, the astronaut, was on the moon. He did an experiment using a hammer and feather in this case, hammer being heavier, feather being lighter. You can find this video, and if you haven't seen it, you might want to stop and go to this video and watch the experiment. It's a demonstration, because he's not measuring anything. He hasn't weighed the hammer, and he hasn't weighed the feather and all of that. He just holds them at the same height, drops them at the same time, and yes, they hit the surface of the moon at about the same time. From that, most people conclude that the acceleration of the objects in the same gravitational field is independent of the mass of the object. Well, you could use a hammer. You do it yourself. Grab a hammer and hold it, kind of hold it. If I can just do it a little bit here. Hold it at the center of this, and hold it balanced. And when you let it fall, I'd try that, but it's takes a while to set that up. But hold it, then let it go, and you'll see that it falls down straight. The head of the hammer, which is heavier, falls down at the same rate as the wood handle. So try it. Yeah, you probably don't have to, because everybody pretty much assumes that's the way it is. So I'm going to start explaining this with starting with Newton's second principle. Newton states that the acceleration is directly proportional to the applied force and is inversely proportional to its mass. That's his second principle. In fact, this is a defining equation as far as any mechanics is concerned. Everything else mechanically follows this principle. Well, the assumption basically, your intuition says that if the mass is heavier, then the acceleration should be faster. Well, for a fixed force, if you keep the force fixed, then you increase the mass, you'll decrease. If you increase the mass, you'll decrease the acceleration. If you decrease the mass, you'll increase the acceleration. Well, that doesn't make sense. We think that a heavier mass ought to accelerate faster, but this says it's slower. It doesn't seem to make sense. But the real question is the gravitational force fixed? Is the force of gravity fixed? So let's take a look at Newton's gravitational equation. Force equals the universal gravitational constant times a large mass times a small mass divided by the distance squared, distance between the center of mass of the object. Says that the force on the object M, force on this object M, is directly proportional to its mass. We generally assume that large M is fixed, small m is moving towards large M, and the force is proportional. So what we're going to do is we're going to take this term, plug it in this one, the term for acceleration, and we end up with g times m, capital M, small m, over r squared divided by m. Yeah, I highlighted m in this, and it's very tempting, okay? Oh, let's just mathematically cancel that out. That's okay mathematically, and I get this. So, okay, well, this, now it says, now the acceleration is independent of mass. That's what it tells you. If this goes up, a doesn't change. M goes down, this goes down, a doesn't change. It's all really based on m, which this says. Well, okay, the acceleration is based on the object that's causing the gravitational force. So Galileo must be right. After the m is canceled out, the equation is for acceleration is this. So now we have the correct value. Mathematically, it gives you the correct value of acceleration for an object that doesn't even exist. We've taken the small one away. Now, this equation does not describe the acceleration of an object. It describes the gravitational field strength caused by mass m at a distance r from the center of that mass. It describes a field strength, not acceleration. And yes, we have in physics a term g, which we use to describe field strength of gravity, the number of g's that astronauts experience when they're pushed off the planet in a space capsule. G is the term used to describe the potential acceleration. Yeah, they're both accelerations. They're both in meters per second squared. But this equation is an equation for one object. One object by itself cannot be accelerated. The m isn't moving, and m isn't there. One object by itself cannot accelerate. You need two objects to have acceleration. Then the smaller object can move towards the larger one, or in reality, they both move towards each other. So let's compare the equation. We have acceleration, which I leave this way with both m's in, and describes acceleration of m toward a small m towards, it's supposed to be a small m, well, assuming m is stationary, then all the acceleration is put on m. This is an equation for the potential acceleration of an unknown object. But any object you want there, it's going to experience this potential force of acceleration. So it's really two different physical equations. Two objects, one object. And the interpretation is the same. The odd thing is, all I did to go from here to here was cancel out to a very valid mathematical operation. Okay, this is a two-body. Okay, it is tempting to cancel out the m, but I'm interested in the physics now of a two-body system, if I'm looking at acceleration. And the question is, how does any theory of gravity explain that the force of gravity increases with an increase of mass? Well, I should have repeated Newton's equation here for the force of gravity. And one could argue the point that, well, look at that. Newton, the force is equal to this, is proportional to the, so as this mass increases, the force increases. It's obvious. Well, that's not quite the same thing as explaining the physics. That's just looking at the math. The particle model suggests that the G1 particle field at the distance r from mass m has a potential to accelerate an object. And it does it this way. An object of higher mass, it's more dense, and with more dense it has less open space, will be hit more often by the G1 particle than an object of lower mass, which is less dense with more open space. Higher mass will be hit more, lower mass will be hit less. Therefore, there is more force on an object of higher mass than there is on an object of lower mass. Okay, I mean, by saying it's independent of mass, you don't even ask the question, is what's the force and how is the force acting? But you got to do that as a scientist, as a physicist. And here's a really kind of a basic problem. The 20th century relies so much on math that the math has become more important than the physics. If the math predicts something, it must be true. I mean, you get the feeling that that's what's happening. If you can cancel out the m in this term, then acceleration is independent of mass, and I can ignore the force. I don't have to worry about it. But as a physicist, I should. So other equations. E equals mc squared. So mass and energy are equivalent and can change from one to the other. I can take this equation, look at it, and I can tell you all kinds of things that this might mean just because I came up with this, or actually Einstein came up with this equation. You have to be careful, because when you mathematically change an equation, you may be mathematically doing it correctly. You can still get the right mathematical value, but your equation may not be describing the same thing you started with. Okay, the conclusion. It seems logical that the acceleration, or illogical, that the acceleration of a larger mass would have the same acceleration as a smaller one. Doesn't make sense to us. The heavier part of the hammer ought to drop first. But that's what experiments show. And people ignore the fact that the gravitational force increases as the mass increases, so they ignore that part of the physics. When you make that statement, when you say it's independent of mass, you're ignoring the force. The particle model can explain how the applied force increases when the mass of the object increases, or vice versa. Your theory of gravity, if you have one, needs to be able to do the same thing. My next video will in fact be on E equals mc squared. Maybe a while before I get that put together, because it has all kinds of different facets that you can look at. If you're new to the particle model, you can view these two videos, or you can go to Particle Guru. This will give you a list of all the videos I've done. I recommend you do that. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.